Okay, hi, I'm Daniel, and welcome to software testing. And this is the course introduction. And as you notice, I'm speaking English for this course. First, let's see if we have someone listening in on the stream, and that can tell us if we have sound on the stream. Thank you. Okay, great. So, course introduction for the software testing course. The content of this one is just to, present me and the course content a little bit, schedule and assignments and stuff like that, course literature, and also what I expect you to do this week and the following day. So my name is Daniel Toll. I'm a programmer. I'm a tester. I would say I was a game developer for a couple of years. I have done a fair bit of research in computer science education. I am also a painter, so this is one of my paintings. So we are going to be a lot of students on this course, 115 students. The course is given for several different study programs and in several different modes. So it's given here in Kalmar, it's given online, and it's given also on campus Växjö. Therefore, with 150 students and one course coordinator, and we need to have a successful communication. So the first way of communicating is the course homepage. It's going to be used for static things that don't change between years. On it, we will place links to the recorded lectures, like this course introduction, links, and some assignment descriptions. In the schedule, you will find deadlines and exams, also the time for the lectures. I just realized that I put links to Zoom in the schedule, but I will try to replace those links with stream links instead to YouTube, so that these lectures are streamed instead of given in Zoom. For all communication with me, except if you're on campus Kalmar, then it is Slack. And I would prefer that 99% of all communication happens in the open channel. So ask questions in the open channel for this course, and about assignments, about missing information or whatever. And I'm always happy for questions. And I would reserve the direct messages for really, really personal things. I mean, if you are having some really personal issue that you don't want to take up with the entire class, then it's a direct message in Slack. Other than that, I mean, all questions on assignments and stuff like that is not, personal. It's not, even if you have your own code. It's not personal. So take those in the open channel, please. So email for really official things. So I'm not a heavy proponent of email at all. Usually I try to check my email a couple of times a week, but it's not the fast way of communicating with me. So Slack is the fast way of communicating with me, and I often forget to check my emails, or don't have time really for checking them. But for really official things, that is important to have an official record for if you're unregistering or something that really, really goes wrong. You can reach out through email. I'm actually going to communicate with you via email soon, before the end of this week. Probably tomorrow, you're going to receive an email for the first assignment. For the first part of the first assignment, you're going to receive a magical link to that one, a personal magical link. But that is the only thing that probably that we're going to communicate through email. So the course homepage is this one. It contains a study guide, of course, the communication strategy that we're talking about now. It contains, a list of the assignments and how I'm going to grade you. A little bit on, what I expect from you. And then we have study guides. And I think these are important for you. So, for instance, the first week, these are the things that would assume you to be working on. So you're right now doing the right thing and listening to the course introduction. And we also have recordings for previous years if you need to, take the course in higher speed or so. But you can also see that there are other things here, recordings on TDD, and we're also going to have tutoring this week. No, I think next week so this is probably not correct. There is a recorded guest lecture with an old student of mine who is a freelance developer, or has been a freelance developer for many years, talking about testing in freelance developing. And there is also a quite old YouTube recording talking about test-driven development. So these are all things that I want you to start. And it also contains reading instruction for each week. But the reading instructions really is pretty simple. It is, this book, and it's 3 chapters each week. So this first week, chapter 1 to 3. Next week, 4 to 6, and so on. It also contains, pre-recorded lectures from previous years, information about the course literature, all the links. But I think all the links that are important are actually in the study guides. So, but you can find them here also. So why not be dry? And there is also information about the different assignments. So for the first assignment that I'm going to email you about, and the second assignment, and so on. Yeah, so that was the course homepage, the schedule. So there are actually different schedules for different classes, but many times they overlap. So, for instance, this lecture or this course introduction is given once here in Kalmar and once in Växjö on Friday. But the next lectures is only going to be given here in Kalmar. So the online students and Växjö students are going to be able to watch them on YouTube, or watch the stream on YouTube live. Yeah. In the schedule, there are also going to be deadlines, and examinations are going to be put there. So they may differ a little bit between these study groups. So check your own schedule to make sure that you attend your own session. This is mostly important actually in January, and not so in this. So yeah, and then I'm a heavy Slack user, and this is our important communication channel. Since we have groups, so many different groups, we need to have one channel for communication. And all the important posts, I'm going to pin those posts so you can see that this post has been pinned, and I expect you to read every pinned post carefully. And whenever you have read them, you react on the pinned post with a thumbs up or thumbs down, or this wizard thing that is so annoying to watch, or whatever emoji you like. Yes, use the public channel for your questions. Okay, so that was the communication strategy. Let's talk about this course. There are a couple of goals that I want everyone to reach before we can put a grade on you. So the first one is to, on your own, automate testing techniques. And this is examined in the 2 assignments, assignment 1 and 2, but it's also examined in assignment 2. Then you should be able to plan, document, and conduct testing of a software. And this is assignment 2. Critically evaluates software testing literature, assignment 3. So present in-depth testing research, assignment 3. And then, explain basic terms and principle, assignment 2, 3, and also the exam. So explain the role of testing and software development, assignment 1, 2, and the exam. So you can see that every goal of the course curricula is covered by the different assignments. And we're going to talk about the different assignments soon. So the first one is to learn how to efficiently use unit testing. And I have 2 different parts of this one. And the first one is for everyone. So everyone needs to do part 1. And then we have a part 2 for higher grade. And there is a quite steep difficulty difference. Now, I wouldn't call it a difficulty difference, but a quite steep amount of work difference, let's say that. So not so much work for assignment 1, part 1, but quite a lot of work for assignment 1, part 2. So if you're aiming for a higher grade in this course, you make sure that you finish the assignment 1, part 1 quite quickly so that you start directly with assignment 1, part 2. So the first one is to learn unit testing with PHP, and probably, or I assume that you don't know PHP right now. And in this CS quiz tool, it's an online tool that you need to use in your browser, and you probably need to use it on a computer in a browser. It contains these small lectures, so, and these lectures should be sufficient to learn just enough PHP so that you can do the assignment itself. And then it contains a couple of practices where you learn how to write unit tests in this PHP language. And the idea here is that the knowledge that you gain from this one should be directly translatable to another language, like JavaScript or Java or C# or anything like that, right? So we are moving to PHP, but the things that you're learning is actually quite the similar things. The functions that you use in these different libraries or different frameworks for testing might differ a little bit. But you should know how to write these tests, and you should also know how to what kind of problems you're going to face, and you're going to start thinking like a tester when you're writing your test cases. So that is the main idea of this. Yeah, it's not designed to be difficult at all, but it can be very difficult if you sort of skip the learning of it. So we've had a couple of students previous years that just skip the learning part and try to do the examination, and of course it's going to be difficult then, right? It's like writing an exam without reading the book. Okay, part 2 is a TDD project. This is a project where you can work in pairs. So the first one you need to work alone. The second one you can work in pairs, but the examination is individual. So here we're gonna be heavily reliant on part of the course literature. And it's this book, Test-Driven Development by Example, quite classic book by Kent Beck. And where you start a small software development project in your own language. You can choose language here, and you can choose frameworks for testing and mocking. And you can choose the tools that you like to use, as long as you are working in the way that this assignment describes. And this one is the in-depth learning how to write unit tests. And I recommend this one to everyone, not only for higher grades, but also that you commit to, I'm going to be good at writing tests. I know some of the students here are already writing tests. And I would say that even if you don't think that I'm going to aim for the higher grade, really, start doing this. You have time within this course to work on this assignment. The part 1 is designed to be short, and then you have time to work on part 2. So I would assume at least all web programmers to do assignment 1, part 2. And everyone who's really okay, I'm going to be a good programmer should do this one. It's going to be examined by oral examination that is going to be booked with me throughout the course. So I'm going to put a booking schedule where you can book a slot where you're having a meeting with me, and it can be I have not really planned it yet, but I'm going to try to squeeze in as many times as possible. But there's going to be a deadline where you need to have booked your session, so to speak. Yeah. Okay. So assignment 1, when you've done it, you should be able to write unit tests. Assignment 2, system testing. This means that we're looking not only at a small part of the program, we're actually trying to look at an entire software. And this one, you're gonna look at, I think I called it testing in the wild or something like that, the assignment, which means that you're looking at an existing open source software project, and you're gonna, examine how they test things. You're gonna conduct their testing first, and then as a second part, you're gonna think about how can I improve this? How can we, what is really missing here? What can we add to this testing? And some of the students from previous years have also, communicated with the developers of these projects and have, improved the testing of these projects. So this is your opportunity to learn how others do it, and then also how to contribute to the open source community, which is an awesome thing. We all rely on open source libraries and tools, so we should also give back to them. But essentially, you're gonna, write test plan, test cases, report, and this is gonna be presented in, I call it a workshop, but it's really mostly you presenting stuff. Short presentations in January, in small groups. And then assignment 3 is non-testing research. And one of the claims on software testing education is that the academy or the universities and the practice of testing is very far away from each other. So if you think about the kind of things or the books that I've taken here are sort of industry books. They are not, science of testing, mostly, I would say. It's more directly for you. Oh my God, the camera got completely confused. Again? Hello? Maybe I'm just gonna pull that one. Get it back working. And let's just see that we have sound. Again, Spazicam. Yeah, it got completely crazy. Okay. And so we have this part of the course which is more directed towards you becoming good testers in the industry. And then we have these other parts of the course that are more academic. And this assignment 3 is to have a peek on what is happening in academy testing, right? So here you can look up and read scientific papers on software testing, or you're supposed to do that, and you're going to present the results or the software testing research to other students, also in small groups in January. So and I think those are really, really interesting, and I think it's also important that you learn how to find and read, and also how to present scientific work, because this is going to be important for you when you have your bachelor thesis. So we need to practice early, so therefore I have added this to my course. So I'm not selecting the papers for you, you're going to search for them yourself and also evaluate yourself. And then we're also going to have the exam, and it's going to be on the books, or it's actually mostly this one, the green one, developer testing, and the lectures. So the course literature is Alexander Tarlinder, Developer Testing, Building Quality into Software. And this book is facing sort of agile testing. It's showing you agile testing. It's not much about testing before agile testing, where we had this waterfall software development method and stuff like that. It's focused on you becoming good testers and understanding how to test your software as a developer. And then we have this other book, Kent Beck, Test-Driven Development by Example. And I would say this book is for you who wants higher grade. And in order to do assignment 1, part 2 for higher grade, you should, work with this book. So we don't have any reading instructions for this book. So you could, work with it and read it while you're doing assignment 1, part 2. You don't need to read the entire book before starting with assignment 1, part 2. It should be enough with the lectures that I give you. But it's good to have this, to read this. And it's okay, because you are students, you're supposed to learn, you're supposed to make mistakes and learn from the mistakes. It's okay to start assignment 1, part 2. Don't really understand TDD. Reading the book while you're doing it, and then, refining how you do TDD so that you understand TDD in the end. Make sense? So don't be afraid to start the assignment 1, part 2. And you're also going to be, I would prefer you to work in pairs, because it's much more fun. Okay, so I made a plan for this course. And the course is really like this. So you're going to start with assignment 1, part 1, when you receive an email, probably tomorrow. And then you have, what's left of this week, the next week, and the week 48. And the deadline is in the schedule for week 48. But you can see that I've planned assignment 1, part 2 to start really next week. So early next week, if you're aiming for the higher grade, I would assume that you're, finishing assignment 1, part 1. So really get started with stuff now. And in week 49, hopefully I'm gonna, be able to produce this booking thing. You need to have booked your examination for assignment 1, part 2. But as you can see, I'm planning to have oral examination in week 50, 51, 2, and 3. And if I can, I will squeeze in some in 48 also. So if you're really, really fast, you can do this. But this one is the expensive examination for me, because I'm going to spend like 30 minutes with each student. And we are 115 students, so it's a lot of time, right? So yeah. Okay, and then we have assignment 2. And in assignment 2, you're going to choose a project, this open source project. In week 50, we're going to, talk about that also. And you can see that if we go down into the tutoring, what I plan for tutoring, the week before, I'm going to, during tutoring time, talk about selecting projects, right? So, and in the middle of assignment 1, part 2, we also have a tutoring that is covering assignment 1, part 2. But for assignment 1, part 1, we only have one tutoring next week. And then week 51, you're going to choose your article. And then during Christmas and everything, you read your article, you make a presentation of that one. You can see that during week 50, we have tutoring time where you're able to ask questions. And I'm also going to give guidance and go through the assignment. So that is the plan. And then you can see a study material, developer testing chapters 1 to 3, guest lectures Max Beppe this week, pre-recorded things, TDD with PHP unit, part 1, and then also this video on test-driven development on YouTube. Yeah, so each week we have a lot of study material, and in January we're gonna have a lot of examinations week 2, and then the online exam week 3. So yeah, we've already covered this one, and then I'm going to talk about CS Quiz a little bit. So CS Quiz is the tool that you're going to be used for assignment 1, part 1. And it's going to be in PHP. And I would assume that, when you're looking at the first parts of it, you're going to be slightly confused, like if I was talking another language, right? So because it's a new language. But PHP is quite simple to learn, and therefore I use it, because it's, yeah. And it also was quite heavily used for web development. So at least you have seen PHP when you're, finishing your study program. The first assignments here that are just used to learn PHP itself. So if you have been working a lot with PHP, you could more or less just skip those. I think it could be good to just do a couple of these in the beginning, even if you know PHP, just to learn the tool, because they are also supposed to show you how to use CS Quiz and how to think about CS Quiz. And then we have this unit testing practice, and then there are two examination assignments. And when you're doing these examination assignments, please note that these are individually, and they should not be shared, and the solutions for those should not be shared, and you're not allowed to use any tools or anything really to solve these. Of course, you're going to be, doing these on your own, but it's on your honor. And when you cheat on this, if you cheat on this, then you are lowering the quality of the students finishing your education. So you're actually shooting yourself, right? So, and they are not designed to be difficult, and every part of them are in the practice assignment. So every little piece of these, so if you're not able to finish the examination things, just go back and go through the different assignments, see what have I missed, right? Yeah. Okay. So actually, it's going to be recorded, the question session. So you are able to ask questions about the course. So I've given the course for 10 years or so. Of course, I try to, change things during these years, but it usually is a quite appreciated course by the students. It's not considered a difficult course, and some students also have heavy study load on the side of this course. This primarily used to be students in Växjö, but therefore I have designed the assignment so that, for instance, assignment 1, part 2 is optional, right? So you can, if you just want to have an E on this course, you can sort of skip it. Okay, so I think that we are going to have a short break, and then we're going to continue in, let's say, 10 minutes. So 22:10, we continue. And Okay, so we are back, and we're going to continue with the first lecture called Basics of Testing. So this is related to the first 3 chapters in that we're going to talk about a lot of different, different vocabulary during this one. So the way that I think about lectures is to give you a language and the language of testing so that you can speak with other testing and so that we can communicate about testing during this course, and also to make it easier for you to read the book. But it is the case, and I've learned from reading several different books on testing and also by interviewing different testers, that there is a lot of different vocabularies. For the same thing, we have different names. So whenever I can, I try to give you more names in the lectures than in the book, right? So the book might have fewer definitions for the same things. But this is something that to look out for a little bit when you go through your and studying for the exam, that I want you to understand that a bug and a defect is the same thing, for instance. Okay, the first part here, so we're going to talk about its testing, and then we're going to discuss faults, errors, failure, infections, propagation, and testability. And then we're going to go into what consists, or what does a test case consist of, and then talking about the input domain, correctness, reliability, all these different testing terms. And I would assume that in order for all of these things to stick, you need to listen to this one a couple of times and maybe make notes of these different terms. So it's not a bad thing. So when you're reading the book, make notes of the different terms, or strike under the different important words so that you know the definitions for these words. Okay, so here is one of the computer games that I did many years ago. I think 2012 or something like that. This is the Time Breaker, and it's an Arkanoid or Breakout clone. The unique selling point of our game was that it was having 3D models that you destroyed with your ball, and these 3D models were animated in 3D. So this truck here, very nicely modeled by me, right, is made out of bricks, and these bricks are, or actually the entire truck is spinning on its own axis. But we are actually playing a 2D game where the ball is colliding with the 2D projection of the 3D model onto the screen, right? So the ball would for instance, break. If it collided here, it would break the back wheel, and if it collided here, it would break the front wheel. So depth is just removed. And we were also, trying to be inventive gameplay-wise, because normally a breakout clone has some kind of pad in the bottom, and this pad allows you to control the ball by, having a little bit of roundness on the edges. But we said, oh, maybe we should have a sphere instead. Like it should be a completely round pad, so that people who are playing the game could be precisely controlling the ball by knowing that the reflection angles of that thing. But we quickly learned that that was too hard for other people, and people don't want to play hard games. They want to play easy games, and they want to have a relaxed time. And then everything in the game changed after that. So we got this colorful theme and everything. But we learned a lot about, or I learned a lot about testing by creating this game. This game took, I think 6 months or so of beside work and beside studies to develop the game fully, so to speak. But when I bought a new laptop, and this laptop had an Intel graphics card, Intel built-in graphics card, I got this. So this was the blue screen of death. This means that Windows itself has crashed. And this means that when you get one of these, your entire Windows installation can, be corrupted because it just dropped out. So stuff that was not saved to disk will not be saved to disk. And it also gave very little information on where you can, debug your game. And it only happened on my laptop. So I needed to find out the reasons for this. And this is a lot of, debugging. Problem was, it happened not every time playing the game. So it was not repeatable. It was not deterministic when the error happened, when the bug appeared, so to speak. So sometimes we're playing the game fine for a couple of hours, and sometimes it crashed in the beginning, sometimes it crashed later in the game, right? So, and I spent 6 months searching for the bug, and I spent, some of the time was, running the game on the laptop enough times to reproduce the bug, and then maybe fix my Windows installation again if it crashed, and then removing something from the game and then run it again to see where the bug is. And a couple of we realized that this only happened with this Intel graphics processing units. And I got the fortunate experience of also talking to the Intel engineers on their drivers and stuff like that to try to solve this problem. After 6 months of debugging, I learned that this problem, or the bug, so to speak, or the fault here, was not in my code either. It was in a specific driver code written by these Intel engineers. And the problem is that, so whatever I removed from my code didn't really matter much. So 6 months of debugging and, starting and reinstalling Windows. And then I found what the bug was. And the bug was that if you loaded a texture into graphics memory, so texture and image really from the game, like the eyes of the robot that you're playing, into video memory, and then you loaded enough of these images before you started using them, you could get a bottleneck where the graphics card was not really loading this into memory when you asked it to, because it was doing what's called lazy loading, which means that I'm not going to load anything into memory until it's used. So if I loaded enough textures into memory, but they were not really loaded into memory, and then I tried to use all of those that were not loaded into memory, and I reached the bottleneck, and then it crashed, or it tried to move enough data to the graphics card, and it cannot do that really. And I learned about that. So the solution was really simple. I checked if we have this driver, then we're just going to use every texture a little time after it's loading into memory. So that's actually loaded. We force it to be loaded into memory. And then I think this was around Christmas, and it was 2012. You can see it here down there. Somewhere around there, I was reading the code for Quake 3, this ID software game. They were pretty big at Doom and Quake games at the time, and they released as open source their source code. And I read this part, which is more or less the same things. Skip Intel workarounds, get tool. So they had essentially the same fix. And I think this was just a couple of weeks from me solving it. So it would be really nice to have read their fix earlier, or if they had released their code earlier. Okay, so what is testing really? So when we test, we want to show that a program does what it's intended to and discover defects, preferably before it's put into use. So I did not want to release my game to the audience before I had solved this problem. A program's, and what it's intended to do is its requirements, right? So we might have some kind of specification with requirements that specifies what it's supposed to do, its expected behavior. When we show that a program does that, it means that we run the program. This is a dynamic behavior. So we don't test stuff statically. We run the program. We start the code. Code is running now on some CPU or in some interpreter, and we get the actual behavior. So we have an expecting and then an actual behavior. And then when we're trying to discover the defects, we really compare the actual with the expected. This means in order to do testing, you need to have an idea on what the program is supposed to do. We can do exploratory testing, or where we try to explore what should the program do. And in games, actually, that is much of the testing that you do. You try to, okay, is this fun? You're really trying out different things. So you are sort of trying out what is a good behavior, because your requirement for a game is usually that the player should have fun. So you're trying to do that. So that in that case, it would be the expected behavior is to have fun, and the actual behavior is that, oh, I'm bored or whatever. Okay, discover defects was comparing these. So a test case itself is specific input and expected output. So what am I going to do to stimulate the system or the program, and what should the program do when I've done that stimulation of it? So when we do that, we check conformance between the system to its specification, to the requirements. So we are comparing sort of a list of requirements with the actual behavior of the program. And if they are conforming with each other, then we say that we have verified the program. So this part of testing is called verification. So I'm checking one list of specification with one actual implementation. When I do that, I build confidence in the software and in the code. For me as a developer, when someone else has learned about us doing it or does it on our game, they also gain confidence. So it could also be done by the customers. So they are checking, I'm getting the thing that I asked for. But it increases our confidence. We learn that we can trust our code when we get this. And this is one important aspect of what testing does and why we do it. So if I just took the game without testing it and, trying to sell it, I would feel a bit anxiety in my stomach that maybe we have a bug somewhere, right? And I imagine that you, as beginner programmers, or, not really beginner programmers anymore, you have written code, you would expect it to work in a specific way, and then you ran the code and it did not work in the way that you specified. Or actually, it worked in the way that you wrote your code, but it did not work in the way that you expected, I mean. Okay, so we want to understand the implemented system. So this could be, does this piece of code work as I think it should work? But it could also be, okay, what has been implemented so far? What parts do we still need to implement? And it could be also to see sort of unexpected or edge cases where we, what happens if we shut down the program before we have done this? Or what happens if I write a too long text here? Will it crash, or what will happen? So this activity of testing gives us a deeper understanding of the system. And when I say system here, I mean the implementation. I mean the source code and its resources that it needs to run. So the system itself here could be a Docker pod. It could be all the configuration of that pod. It could be all the source code, or it could be different compiled units. It could be the different libraries that you have included, its dependencies and stuff like that. But I say here, then the next part, but also the requirements and how they can fulfill the customer's needs. And this is a second activity called validation. So if I'm thinking about what makes a good game, or what makes a game fun, then I'm actually trying, the kind of testing that I'm doing is called validation, right? So I'm trying to think about, am I doing the the right product. Are we building the right product? Is the definition by Boehm in 79. So when we're doing validation, we demonstrate that the product meets the customer's expectations and needs. This means that is the game fun for these customers? And not really does it conform to a specific specification, which was this verification stuff. We have a higher level focus. We focus on needs and expectation, and we think stuff like, okay, is this a good way of doing this or not? So you run the program in the way that it has been written, but you think like, okay, I'm going to be the customer running this program every day. Maybe if we swap out the ways of input here, we can reduce the number of clicks or something like that. Then we're in validation mode, where we're really actually designing the software when we're doing validation. Okay, usually in software processes, this validation thing comes down to, okay, we need one test for each feature to make sure that that feature has been implemented, and that so that we can run these tests with the customer, for instance, and we can make sure that the customer sees that it is what it expects. So if we create a suite of tests with one test per each feature, we could call that an acceptance test. And the one who accepts the product is usually the one who orders it, or the customer, right? So we can let the customer go through this acceptance test, and they say, okay, yeah, we can, authenticate in the system, we can order products, we can pay for the product, and we're actually going to receive an order in the end, or something like that. That could be acceptance test. So validation sort of goes from something very, very fuzzy, and that is the needs and expectation of customers, and tries to make that more solid, so to speak, so that it can be communicated to the developers and communicated. Maybe we're writing it down as part of the specification. But the needs, or what a customer thinks is fun in a game, this may be different for different customers also. So this will always be a little bit fuzzy. And just because we understand one customer doesn't mean that we understand them all. So we might have testing activities like beta testing or something like that to understand a larger population of customers. But we need to understand the overlap really between the implementation that we made and the needs and expectation of the customer. Is it good enough? Does it solve the problem that we intended to solve? Do we do this in a really good way for this particular? Do we earn money, for instance, could be one validation question. It's a lot about communication. It's a lot about, someone needs to communicate or the customer needs to communicate their needs and expectations to us. And one easy way of communication is to receive a product, and they test out the product in this way, and they say, no, this was not what I expected. This does not solve my problem, or this solves my problem. It's much easier to get that. So I would recommend, if you're working with customers, to really, really early in the project, give them a prototype. Give them an interface to work with, so that you can talk about this interface. Does this solve your problem? Is this the way that you expected it to be? Even if things behind the user interface does not work yet, you can, really catch more of the requirements or understand. Okay, the verification part then is this: are we building the product right, but in the right way? I would say same person defining the term. So we check that the software meets its stated functional and non-functional requirements. We try to go through the different requirements, and we carefully, construct tests so that we know if this requirement has been implemented in the way that we specified. So we try to find faults in the code by finding some input for which the behavior of the system is incorrect. So this is much lower level focus. So validation was high level focus. We're thinking about, the needs and expectations. Here we're thinking about, okay, does it match this specification? Are we, and usually I would say the verification part of it is a bit, testing smaller parts of the program, I would say. Really what we're asking is, does the implementation A implement the requirement R correctly? There is a word called program verification or formal verification. And this is actually something else. So if you're, Googling on verification and you find something that is, seems to be a mathematical proof for if something works or not, then this is not the same thing as verification. I would say it's connected. The program verification, when we do this mathematical proofs, and there are, tools to work with and ways of doing this, what we're really doing there is that we show that there is no error for any input. That is a mathematical proof for that one. But when we're doing testing, we're actually not in that, even close to that one. We're just trying out different inputs, and we see if they work for these inputs as expected. Okay, so we have a developer on the left here, happy developer. And this developer writes some, or has an idea of a product, and it's represented by this orange rectangle and the circle. And the needs and expectations is this idea, right? So it's in the head of the developer. And then the developer writes this specification, an orange rectangle, at this sizes perhaps, and then a green circle with a specific radius is drawn on top of that one. So it's on top of that one, which means that it's overlaid, right? And then we have a developer here on the right who interprets the specification and does not interpret overlaid. It interprets on top of, as the green circle should be on top of it. It should be above it, right? Make sense? Or doesn't make sense, actually. This is a misunderstanding. So this is the first misunderstanding that we have. And then the programmer writes code. And the code actually does something else, right? This is our, buggy code. So it's almost on top, but it's actually behind also. So it's somewhere in between. And then maybe the first developer also, who was responsible for the specification, also writes a test for this one. And the first developer writes the test like this. We expect the rectangle to be of this color. This is actually what is important to me. It should be this specific color of orange. The RGB values should be 255, 153, and 0. And this test will only find bugs related to color. It will not find the bug related to the, where the circle is placed. So it will not find the misunderstanding. It will not find the misunderstanding and will not find the misimplementation. Okay, so when we're specifying something and then we are implementing something, we are trying by testing, or the verification part of that is to see the overlap of these two. Which means that only in the inner circle here, we can find bugs. So the faults or the bugs or the defects, which is the same thing, needs to be a part of the specification that is not as it should be, not as it's expected in the implementation. But you can see here, we can also have parts of the specification not yet implemented. So the blue parts here are stuff in the specification that says it so in the specification, but we have no implementation for this. So this could be a requirement that we have not yet implemented, and we call that omissions. We can detect faults of omissions by testing. So we write a test case for something. It's not been implemented yet. We run the test case, and the test case says this test fails, and the reason for its failing is that it's a fault of omission, which means that not yet implemented. Then it gets a little bit more interesting, because we can also have surprises, and that is stuff that we have implemented that is not part of the specification. I remember a really cool developer once who made this really, really nice systems where you could edit images in like Photoshop, And at the same time as you edit them, they were also changed in the game that he was writing, right? So there were 3D textures on a building, and he could, work in Photoshop on this, and it would just change in the game simultaneously. So we could have, and this could also be done as a multiplayer thing. So there was this Photoshop plugin, there was this framework for a game development that he had developed. But he also showed that if I click on this red pixel here that seems to be out of place, then I get I think it was like Asteroids game just popping up. So the Asteroids game itself was just an Easter egg. So it was a surprise, right? It was not part of this thing. It was something that this developer just developed out of having fun, perhaps, or too much creativity or whatever. But it was not in the specification of the product, so to speak. This was not what the customer expected, not fulfilling the customer's need. So we could call such things surprises. And okay, now you think that seems to be stupid to implement this. It will cost resources and stuff like that. But it could also be stuff that just exists there because we have used this library, and we get this useful component from the library, but we also get other uses for this library. And I bet that every one of you have done this because you have copied an old assignment and you started a new assignment. And while you were thinking, I'm going to remove stuff from the old assignment from the new assignment later on, but while I'm working here, I don't want to be bothered by that. So you've also had these kind of Easter eggs in your implementations. Is this an assumption that is correct? Yeah. Okay, so you have also created surprises, but it could also be surprises out of mistake, right? So we could implement new behavior in the program or in the system that we would be surprised of. Just so. And then we have two different concepts. We have testing and checking. And testing is to come up with a test. Thinking about how am I going to test this feature? Or thinking about how can I test if this game is fun? Or, the validation or verification. It's a creative process. So you think about what should I test? What are my goals here? What requirements or what code am I trying to test? What part of the system should I include here? What input should I have? What is the expected behavior of this one? So this is actually designing tests. So when you're testing, you're designing tests. And then we have running the tests, and that is called checking. You run the tests, you start up the program, you input the behavior, and you input the input, and you check the behavior, the actual behavior. And checking itself, many people think testing is boring. It's because checking can be boring. But the first thing, I think that it's exciting, that is a creative thing, and it has value. And when you do the first thing, I think that you can feel the value if you do it right? But when you're doing the checking thing for the 100th time, and for my games that I've developed, I loved the games before. I loved the games when I developed it, right? So and then I tested it over and over and over again. And if you develop something for 6 months and you run, this breakout clone or whatever, you become really, really good at playing that game. But you also get really, really bored by that game because you're playing it like 10 hours a day, or these things. So checking can be quite boring. And if something is boring, it should be a hint to ourselves that we want to automate this. And much of testing today and out in the industry today, you are supposed to automate your testing. And during this course, in assignment 1, part 1 and part 2, we learn about automating things. And assignment 2, there is also a big focus on automation. And maybe there are checking problems that you can automate. And the reason that we want to automate is not only that it's boring to do the same thing over and over again. It can actually be quite fun. I'm quite good at doing boring stuff, like checking exams or stuff like that. I'm quite good at it, crunching through boring stuff, and I can motivate myself that it's important that I do this thing, and it's important that I go through all of this. But I would like to spend my time doing testing instead, the creative stuff. Yeah. Okay, so conclusion for the first part is that testing is to come up with ways to exercise, or the exercise is another word for running the system. And the aim is to find these faults. Testing is dynamic, even though the quality requirements might use static testing tools. So dynamic means that we run the system and we examine what happens when the system runs. Checking was when we enter input, we compare expected behavior to actual behavior. And then we have this, validation thing, which was, I would say the validation thing, if we're doing it right, we're always doing testing, more or less. It's more general goal directed. And we have verification, conformance to requirements. Okay, so I think that we're going to have just 5-minute break. So 10:15, we're going to continue with faults, error state, failure, infection, propagation, and testability.
Du sa ju att du...
Ja, vi kör. Okay, so we're going to continue the lecture with more definitions. So fault, error state, failure, infection, propagation, and testability. So fault or defect or bug is the same thing. So many different definitions for the same thing, though. So fault is a static flaw in the program code or state. So program code, I mean, that is, JavaScript or Java or PHP or whatever you're writing, right? It could also be a problem in the state, configuration of the program. Its environment variables, its database, its persistence, etc. I mean, it could also be a bug in someone else's code. So it doesn't need to be your code, really. So remember the case where the Intel programmers have written this faulty driver, and not me, really. So we usually think of that as a bug, but these other names are also used. I think the book calls it fault. So check out this little program code. So we have the add method. It should add numbers A and B together with an addition. Here we have return A minus B. The minus sign should not be there. It should be a plus sign, right? So the minus sign itself is the static fault. It should be changed to a plus sign to get all the tests of this function to go from a failure to a success. The original bug was actually a moth. So in the beginning of computers, we had these mechanical relays. And a relay is really a mechanical switch. So you have a magnetic coil. And if you run current through the magnetic coil, it becomes magnetic, right? So it's going to close a switch. And if you close the switch and there is a bug sitting on a moth on it, the current cannot go through the closed switch. So this is the original bug, and you can see it here on the... Okay, so next definition, error state. So program state, to begin with, is all the dynamic content, so to speak, all the values in memory and storage. So all the... if you have a variable called username, its value is part of the state. But also everything in your database. Also everything, if you connect your system through an API to other people's databases and stuff like that, then their state also. So every state... Okay, thank you very much for blocking ads. Very happy for that. But it could also be, every integer that you defined, every file that your program is going to run is the state. It could be, we could go even fuzzier and say that the time of day and stuff like that is also state, if you include a clock into your program, sort of the state. Okay. So here I define a variable A. It's an integer. I give it value 3. So after running that line, now we have somewhere a variable in memory, and its value going to be A. But there could be other values also here. So this is a collection of all the variables. So an error state is a bad, illegal program state that results from a fault. So just imagine now that we run the add method from the previous slide with its minus sign instead. Sum will, after that addition here, so 3 minus 4 is going to be minus 1, right? So sum is now going to be minus 1 instead of the correct state, which would be 7. So now sum is in error state. It has been infected by the bug in add. So it can happen that we run code with a bug in it, but we still don't produce an error. So we still have a correct state, right? So imagine that we run add with its minus sign. 3 minus 0 is still 3, because 3 minus 0 and 3 plus 0 is 3, right? So even if we run a code with a bug, we don't get an infection. We don't get an error state. So in order to test things, in order to find faults with tests, we need to run the code with the defect. That means that we need to find a way to stimulate our program so that code is run, right? So we need to reach that, the location of the fault. So it could be as easily as, we write a piece of code and we call the function add. So if add is not called at all, we will not find the fault. Okay, the infection part was that the fault must alter the program state into a bad one, into an error state. So in order to do that for the add method needs to be called with a non-zero b, right? So if you look at this one, if the b is 0, we will never discover the defect here. So this b must be something else than 0. We could actually put whatever there and we will detect it. Finally, we need something else in order to detect the error. The error state must at some point produce an incorrect output. That is an observable failure. So we must show the output of add to the user. If it's not shown, we will not detect the fault. In some means, it needs to show it. Sometimes, this addition will just, happen in the background where we will never notice. So think about a banking system that, has a little bit error in its calculation, and the bank account. If no one checks the bank account, we will not detect that we have this problem. So, needs to propagate. I think that all of these things, reachability, infection, and propagation, are important because this builds testability. Okay, failure then. It's an observable, incorrect behavior of a program as a result of a state. So first, again, not every error state ever surfaces to the output, to the screens, or to a printed output. And then not every failure is observed either. I mean, if the change of the addition thing, there was this, it's not actually a bug because it was intended, right? People were stealing money from banks by taking really, really, really small parts of a transaction and putting it on its own account, right? So if you add 3,000 kronas with 2,596 or something like that, and I steal 0.01 öre from that transaction, maybe you won't notice because it's so small, right? So you might not notice. And in this case, on the screen, we have two orange rectangles. Are they the same color? So even if one of those are in error state, we have a hard time detecting if that's the case. Of course, we could do stuff like, okay, I take a screenshot of this, I open Photoshop, and I check the RGB values of these. So there are possible ways of doing this, but it's not easy at least for me, I don't see a difference here. But there is a difference between these two. I've constructed it that way. So some are very hard to observe. And like these colors, we're not really good at differentiating between colors that are so close to each other, or very small differences in numbers also. We might not detect the 0.001 or might not even care about that. But in testing, we want to observe failures. This means that we want to create mechanisms in our program so that we can observe the failures. We sort of want to open up the program a little bit so that we can see the inside of it. We want to make sure that our code is correct, and these error states might be hidden in databases and stuff like that. So we might want to open them up and inspect them. Okay, so a goal of a test case is to do all of that, the controllability, to be able to to steer a program to run a specific, okay, I want to run the add method now. How can I run the add method? Maybe I need to log into this system and I need to go to this sub-menu, and then I run this with a non-zero B or something like that. So I need to steer the program to that point. So if I cannot easily steer the program to that point, it's not going to be easily tested. There are many cases that we create really hard to test code because we don't have mechanisms to control the flow of the program. So we need to reach the fault, run the code with a bug, produce an error state, and make the error visible as a failure. All of these things from the previous slides. And then we have this other thing that we want to have also, observability. We want the ability to see what the application is doing. And if we have both of these, we have testability. So controllability plus observability means testability. So reachability, infection, and propagation was part of the controllability, right? And then observability, we also need that. So if I have those things, and I also know what the base or the baseline truth is, then I can do testing. Because if you don't understand what is this software supposed to do, then I'm unable to do testing. So we would need some kind of specification or requirements to understand that this is, what is the expected behavior. Because that part of it, we can get the actual behavior, but we cannot get the expected behavior unless we have that. And now you're thinking that, oh, maybe, but I use a lot of different programs, and I, understand how they are supposed to work just from the program. So if you start a game and you're not having fun, you can still, say that this is a test result. I'm not having fun playing this. Or if the game is some character jumping on platforms and it's suddenly falling through a platform, you realize this is not what it's supposed to do, because you've run these platformer games before, and you should be able to stand on a platform. So you can have an informal specification, or you can have your expectations about something still. Okay, we have other goals from test cases, and one of those goals is that we want to find where the bug is. We want to have an accuracy of our test, and this is how can we isolate the faulty code from the correct code. So if I run 10,000 line program and I get an error state and I detect that, I get an observable failure, I might not know which part of this 10,000 line code that was containing the failure itself. So the accuracy is how well I can find, how well I can isolate the faulty code from the correct one. So it's almost always better to run just a few lines of code around the failure, or no, around the fault, around the bug. We would prefer to do that because it gives us higher accuracy. And this is one of the reasons that unit testing is so popular, because we can write a piece of code testing another piece of code, and we're just calling one method in this test case. Secondly, we want to have traceability. So we want to connect a failing test case to a specific piece of code. And this traceability, this code was run, is not always easy. So think about the problem that I had. I was running my code, of course, when I was searching for the blue screen of death bug, but I was also running code from other developers, libraries and drivers and stuff that I did not have control over. So one big thing, and the reason that it took 6 months for me to find this, was that it was not in my code. So I did not have good traceability between the sort of the test that I ran to the code that was actually causing the problem. So it can be a traceability between test case and code, and test case and requirement specification also. Sometimes we add and remove requirements from an app or from a program. So if I remove a requirement from a program, I also want to have traceability between the test cases to, that requirement covered. On the other way around, that I want to have traceability between the requirements and its tests. So if I remove that requirement, I can just remove all those tests also, because it's no longer valid to run those tests. Okay, conclusion here. Fault is the static bug that can lead to an error state if it's executed. This was the reachability. A fault infects the state, and that changes it to an illegal one, the error state. For the error state to be detected, it must be observable. And we need to get a failure. That means that we observe the error state. And when we observe an error state, we must also understand that this is an error state. We make a judgment that this is not what I expect. This is not the sum on my bank account that I would expect, or this is not the right kind of orange color. So the next part continues this. So we're going to talk about test cases, input domain, correctness, and reliability. So first, a test case. So on the top here, we have some code. It's the add method again, and this time in some weird programming language, some looking a little bit like PHP, but I've removed some characters from it. But it takes two numbers, x and y, and it has a fault in it, the minus sign. It should be a plus sign, really. And then I have a test case, and this is input for each of the arguments of the system under test. And it's also contains the expected value. So we have 3 and 2, and we have 5, because 3 plus 2 is 5. So we exercise the system under test by running the system under test, or exercising it with the inputs, and then we get an actual output. And you can see it down here. I just have an if statement that checks if the actual is as the expected, then I output it works. So this one has almost all of the requirements for a good test case, because this is observability. If it says it works, then we know that, okay, the add method does not have an error state, or does not have a do an infection for this specific input. But if we get an error state, it will not output it works. So I would increase this little example like having an else statement here. In JavaScript, it can look like this. Describe when a JS file starts to use Babel, it translates it to Babel, and then it uses this piece of code, and then I expect something to be something else. If I have Java, then I can say that I would expect this piece of code to throw an exception. And this is for C# also, so we can have, we assert that, this is actually a test with multiple inputs and stuff like that, but it's not that really that different. So there are a lot of these different ways of writing tests, and for each of these frameworks, we need to learn the framework, of course, to master that and run the test in that. The test case itself needs to have these things. It needs to have a system under test. And the system under test, it's the collection name for everything like function under test or unit under test or whatever. So I call that system under test. And what we're saying is that this is the thing that I'm testing. This is the method that I'm testing. This is the object that I'm testing. Usually, if we have an object-oriented program, I create an entity class that we're testing, and I call that SUT, or system under test. This is the thing that I'm testing. If I'm only testing the add method, then really the system under test is the constructor plus the add method, because it's not that easy to differentiate between these two. Then I need explicit input. That means exact values of x and y. And I mean explicit, and as we need to define these values. This was one of the most common errors that beginner testers do. They say, input a number for X and input a number for Y. If we have this fuzzy input a number thing, people can input 0 as B, and we will not detect the problem, right? And some other tester interprets the instruction like, okay, I'm going to have 5 as B. And that tester will detect the bug. But these two testers are now not aligned, really, with their... So one tester thinks that this system works, and the other tester says that this system does not work. Okay, so we need to have specific inputs and specific outputs. We need to say it should output a 5. We cannot say it should output, you know, a number or the sum. If we're just saying it should output the sum of the two inputs, then we're actually, the test and the specification is the same thing. So be clear on how you test. Okay, then we get the actual output behavior, what this SUT actually produced when giving input, and then we need this mechanism of observation, the if statement and the comparison and the echo, the system out print line thing. Okay, and then we observe. And when we observe, we make a judgment. So when we make this judgment, we are the ones that are called the oracle. So the oracle, this is from Greek mythology. So the oracle itself decides if the observed behavior matches the expected behavior. And in some cases, this is, you know, not easy. So let's have these two orange rectangles again. So everyone in the classroom raise a hand if you think these are the same. Yeah, 1 out of 10. And everyone that does not agree that these are the same, raise their hand. Okay, so now we have 9, right? Something like that. 8, actually. So 1 out of 8 thinks that these are the same, and then 7 out of 8 thinks that these are not the same. So let's say like this. Let's talk about the requirements a little bit. Does it matter that these two are not the same color? How many thinks that it matters that these are not the same color? No one? No. Probably does not matter. If this was, you know, the background color of a website, no one would notice. So it doesn't matter. Now, the same thing. How many thinks that these are the same? Again, 1. It doesn't matter. So it's the same, because for the, you know, for this application, it doesn't matter. So we would say the correct answer here is that they are the same. And the decision that we make here is the oracle decision. We decide if the observed behavior matches the expected behavior. So actually, the colors themselves are not the same, but it doesn't matter. So they are same enough, right? It's good enough, so to speak. So the oracle is the source of truth, and this is actually what we humans are good at. And I think that this is perhaps why testing is more important now than it has been during the last years. Because now we're going to have a lot of generated code. And we as humans need to give our judgments. Is this code good enough? We still need to be the oracles here. We need to create the test cases. We need to think about, all this. Do we get our value from this? Is this fun? Is this fun enough? Okay. This is just another way of expressing a lot of the different things that we've learned so far. So think about the programmer up here, writes a code, and the code itself, I call that program here. I previously called it system. The programmer might have an error in thought or action, so I can misunderstand the requirements, for instance, or I'm just, writing my code in a bad way or something like that. We make mistakes. That is called an error, by the way. It's not, so a fault and an error is not the same thing. The fault is the bug, the part of the static part of the code that needs to change to get the correct code. An error is something I did, right? So it may lead to a fault. And then we have this program, and the program produces actual output and behavior. We use the specification up here to write the program. And the specifications themselves determine the expected output or desired behavior of the system. And then we have the observed output behavior and the expected behavior, and the oracle says these are the same or these are not the same. Okay, a lot of definitions here. Something that is important for testing is reproducibility. We want to run the same code under the same condition and get the same results. So we run a test, and we want to be able to run the test, and every time we get an observed failure or that the test passed. Either one. We don't want these to flip between, sometimes it passes, sometimes it doesn't pass. So one of the problems that I had with the game that crashed with the blue screen of death was that it was not easily reproduced. I needed to run the program over and over and over and over again to be convinced that I've solved the problem. And if it's just sometimes that it happens, under specific conditions. And it seems that it had to do with the load of the CPU of my laptop and stuff like that. And sometimes Windows was doing stuff in the background, so the loading of the textures took a little bit longer time, and then the game worked. So we want to run test deterministic and get the same result for the same input. I once interviewed a lot of testers, and one of the testers said that, and this was a bit earlier than agile testing, and they were not so close to agile testing in their company, because the developer were testing code and they were finding problems in the code, right? So the test failed, and then they gave this list of failing tests to the developers of the system, and the developers ran the tests, and they said, no, it did not fail. I just ran the test, it worked for me. And I bet that you have done this. It works locally on my machine, it works. So there is no problem in this code. Could be a problem in the configuration, perhaps, but it's not my problem. So we call tests that flip between successful and failures. We call them flaky tests. And these are really, really bad because they cost a lot of time. So they cost time to investigate, and we can, argue about these tests. It works, it doesn't work, it works, And in order to go from flaky tests into deterministic tests, which are good, we want to have the same output every time, we need to control the program state. So for me, in my case, I sort of would have needed to create this perfect condition where the CPU was always working in the same way and Windows were never acting up against me, so that I could reproduce the bug over and over again. That was not easily made, right? So for some tests, it's not easily done to control a program state. You want to be able to control like timing database and stuff like that. And if you think about a unit, like the add method or a function that you've written, if this function connects to a time, to a clock, and has different behaviors at different times of day, then your test might give different results at different times of day also, because you have an input that is from the clock of the computer. Or if you're talking to an API, if that API works in different ways at different times of day, or you have the data in the database is changing and stuff like that, then suddenly you can get flaky tests from this. So you want to be able to control that in order to get reproducibility and not flaky tests. And another way is this interpretation of the test case itself. You want to have explicit input, or specific input, I would call it today. And finally, we need to agree on how the Oracle decision is made. So it's really good if we can do all of these things in our tests, so that we get reproducibility. So the assert, or the if statement that compares the actual and expected, if we have that if statement as code, then we have made this reproducible, because it's always going to be compared in the same way. So if I compare the two colors of orange in an if statement, and I say that they need to be within like 5 color points of each other, at most 5 color points, then I'm okay. That would be one way of saving the Oracle decision. Yeah. Okay, so here we have a manual test case. Navigate to page. It's just to open up a browser, input the URL, and we would look at the page. And the things that should be, we should clear existing cookies to make sure that we have a reproducible way, because this application was built on cookies and have different behavior. If you had the cookies, you could be, for instance, having a session cookie that was showing that you were logged in, for instance. And so you need to clear your cookies, and then you navigate to site, or in the other way around. And the expected output was that the text not logged in is shown, a form for login is shown, and today's date and time. So some of you might have seen this before in 613 course. And the interesting for me was that, and then just to make the output or even more clear, I included a screenshot in this manual test case. So the screenshot was down here. And I found out this was a really ambiguous test case. It's super simple, but students running this test case on the same software were getting different results. Why? So some students did look at the instruction and say, okay, it should say exactly this. But on my system, it gave me today's date. And that is a misinterpretation of the actual test case, right? Hopefully you understand that we should have today's time and not, this. It could, of course, be even more clear. Today's date is shown. This is just an example. On your system, it will say something with, this year's year and stuff like that. We can be overly clear in our communication. But there was also another thing. There was a true bug, a true fault. And only one student out of the students found the true fault. So this student checked out on Sundays. It actually didn't say the day of week. So on Sundays, the system was not behaving. All the other days, Monday to Saturday, it behaved correctly. But on Sundays, it did not output Sunday. And this was because I had misinterpreted the specification of the date function, or the date to string function. So 60% assumed the test case was correct of the students. 1 out of 65 found a bug above. And it was my fault. I was the developer. I misread the documentation. And then we looked at different test cases. I found out for almost every manual test case that I wrote, students came up with different results. And of course, there are reasons for these different results. And the reasons that I could find was at least this: time of day, variation of testing condition. This is really input that we could not control. Timing, so we perhaps, be very fast at clicking. So I click super fast, and I get a different behavior than someone who clicks slow. We could have environments. So if you run a program on a specific in a specific browser, for instance, I get, a different result. The order of the test cases. So if you run a specific test case before this one, you could get another result because you have a different state. So you need to reset state between these. Also, ambiguous test cases, language, interpretation, all of these things. So it could also be, the tester is actually, not really reading, just thinks that it did read, or, doesn't care really. That could also be a case. Faulty test cases are also, if you follow the test case precisely, you will get different results. Or, the error could also be in the test case itself. And the conclusion that I came up with was, okay, it's not a sign of bad programmers, it's a sign of miscommunication. Yeah. Okay, I think that we should have a break. So let's take 10 minutes now and continue 11. Okay, let's go again. Continue with more definitions. And now we're getting slightly mathematical. So think about a function. Could really be a function could really be an entire program. But let's simplify it to the add method for now. So think about all the different inputs that we could send to the add method. Could be, 0, 0 or something like that, or 0, 1, 0, 2, 1, 0, 1, 1, 2, 2, 1, 3, 1, all the different combinations here. So that would mean that if we collect all of those inputs and all the expected outputs for those, then that is the, no, not the expected output, all the different inputs, that is the input domain of that function. So the domain contains all possible variants. This depends on how large integer we are using for the add method, right? So if we're using a 32-bit integer for A and B, the different inputs into the add method, then we would have 2.1 billion times 2.1 billion different combinations in the input domain. Make sense? So let's imagine that we randomly select a number of those. We randomly select perhaps 1,000 of those. And we count for how many times the add method works, sort of according to the expected value, and how many times we get a failure. And the times that it works is the reliability of it. It's sort of the percentage of a random input, if we run the random input a lot of times, and the percentage of those times that it works. So then we can calculate the reliability of the program. It's sort of a measure on how often it works. Okay, and then we have correctness. And correctness is actually not a goal for testing. But if it worked for any input, so all the different combinations, then we would say the program is correct. We can think about the different ways of interpreting this. So the add method itself, A plus B, the correct one, is it really correct? What happens if I input a 32-bit number and another 32-bit number, and their addition is larger than 32 bits? Is it still correct? Maybe a correct version of add would throw an exception if A and B together is larger than a 32-bit number can be. We would have a number overflow, right? So maybe a correct one would be that. So those are a couple of definitions that I think is important. And one of the interesting problems that comes or stems from this is the test selection problem. So if I test everything, that is called exhaustive testing. It is impossible for most applications. So, and it's not needed either to find the faults in the application. So a 32-bit number goes from minus 2.1 billion to 2.1 billion. Input domain for this super simple function is 2 to the power of 32 times 2 to the power of 32. It's an insanely large number. Can we exhaustively test add method? Do we have time to do that on today's CPUs? No, it will take forever. So with testing, we cannot prove correctness. We could prove correctness if you write a function that has super simple or super small input domain. let's imagine that we have a function that takes a Boolean and returns some value depending on that Boolean. Of course, there are just 2 test cases for this one. So for this trivial function, we can prove correctness. But for most functions, or if I have some other kinds of input, clock time or database or hidden dependency or whatever, suddenly the input domain is actually larger. Please note that even stuff that does not go through the arguments to a function can still be the input domain. So if your code reads from a database, the input domain is all the possible results it could get from any database, right? So, yeah. Okay, so exhaustive testing is impossible for most applications. And I just want to say that if we have different testing goals, so to speak, we want to have different efforts in our means of seeing if this is correct or not. So in this first one, this is Age of Conan from 2011. And when it was released, it was ridiculous because it had so many bugs in it. And one of the more fun bugs I thought was that, your horse was invisible, for instance. So you could sit up on your horse and it was not showing. So the testing for this program was, of course, not enough, but perhaps it was enough for a game. I'm not sure if it was a commercial success still, and I think in the gaming industry it still has these really big quality problems. There are these super huge AAA titles getting released that are having too serious bugs in them. I don't know if you suffer from this, but a lot of people. If you're launching a rocket into space, and this rocket costs 5 billion or something like that, of course you want to be more thorough with your testing. Of course you want to do other means of or more carefully test your program. So this is the Ariane 5 rocket. When it was launched, it had a bug in its code, and I think it was one of those translating between different number formats bug. But the rocket decided that it's a good idea to make a 90-degree turn now in the middle of Mach 5 or something like that. And it's not a good idea. It will blow up, right? And it did. So, of course, if the purpose or the goal of the software itself, it determines the testing effort. If it's going to be people involved, if it's a self-driving car or whatever, of course, you need to do more thorough testing. But if it's a game or it's a school assignment, maybe it's not that big a deal if a test case fails or if you have a missing test case. Okay, now let's go to test levels and test types. So there are different levels of types, and these levels are how much of the program that we're testing, sort of, but I've also included the later ones here that has to do with perhaps not really test levels, but it's on the same slide for some reason. So let's start with the first test level, and that is unit testing. We test a small piece of your program. We call that the unit. And it could be a method. And usually I have a unit test per method of my program. Sometimes we say that the unit is a class. And we say that, okay, this class has one test case or a couple of test cases for this class. It could also be a component. So we write unit test for a specific component. So all this method, class, or component could be unit. So if you determine this is my unit, then I write a test for it that is called unit tests. Usually, unit testing is also connected to automated unit testing frameworks, like JUnit or Jest or these frameworks where we can easily write these, where we get some support for writing these. The next test level is a bit bigger. It is testing. It's called integration testing. It's testing what happens when we put units together. So I'm testing this unit and this other unit together. And this could be different parts of your program, for instance, the back end and the front end of your program. And when you're testing how they integrate with each other, we can call that integration tests. These tests usually are bigger, more complex, and take longer time to run. The unit tests are designed to be small, have a high accuracy, which means that we know that we're just testing this small part of the code. If it breaks, the fault is in that code. Integration tests can be much larger. We could test, the entire backend, for instance. And then we have the largest part of this called system testing. Here we run multiple components together, or perhaps all the components together. So this could be backend plus frontend again, but we say now we run the program as a program, all parts in it. So we call that system testing. And one way of doing system testing together with customers is called beta testing. So beta testing is when we take a system and we create this testing environment and we invite people to use it. And this is most commonly used to attract early adopters to our system. So we really want to get the people who are most interested to test our system first, because they can be a bit more reliant and maybe ignore the bugs that you have in beta testing. In gaming industry, I've learned that this is not really testing at all. It's just commercial. They're just trying to attract people to their game, making buzz about the game, because the game development is so far away from the beta testing version. So even if they find bugs in beta testing, those bugs are no longer in production version, or the ones that they are working on, for instance. We've already covered acceptance testing, and this is also a part of system testing, or a way of doing system testing with the customer. Yeah, we give the software to the customer and let them test it, and we call that acceptance testing. Usually, what I mean here is user acceptance testing also, just to confuse things a little bit, because accepting testing can also be that we write a number of test cases where we try to cover the entire application. Yeah. And then regression testing. This is not actually a test level per se, but a way of running tests. Whenever we run tests that we've run before, after a change, we are doing what's called regression testing. That means that we have previously tested this, maybe we got a failure, and now I change the source code and I run the test case again. I regress, I run the test case again. Then we have different testing types: black box testing, white box testing, smoke testing, and random testing. As examples, there are, of course, many more. So black box testing is a way of thinking when you write your tests. And the way that you think is that I don't need to understand what's on the inside of the thing that I'm testing. I'm just thinking of the thing as its requirements and its expected behavior. What kind of input can I send in, and what should I expect out of it? So you're not really looking on what happens on the inside of the code, of the source code. You're trying to find, going from the input domain and finding different interesting inputs, and perhaps also the output domain. More derived from the specification. So, and then the contrast to that is white, or it's also called glass box testing. If you have knowledge of the source code, you can write tests from that. So if you look at the code example, you don't really need to read it, but you can see that there are a lot of if statements. So if I'm going to test this code, I want to make sure that I write test cases that goes into those if statements, and perhaps different combination of if statements. So maybe I go into the first one, and then I have another test case that goes into the second one, and then I have another test case that goes into the third one, and then I have a test case that goes into this one, and this one, and this one, and this one. And then, yeah, something like that. So I'm using my knowledge of the source code to guide my testing. I use tools like code coverage in order to find test cases that I need to write. Then I'm doing white box testing or glass box testing. And then we have smoke and random testing. So these ways of testing are more based on randomizing or just running the system and see if it breaks. These are really good for some kinds of systems like compilers or where it's easy to judge if the output is in an error state, like if you get a crash. So if it's easy to understand if the program crashed or not, then we can do this. So let's begin with smoke testing. In smoke testing, we try to run as large part of the system as possible, and then we look for smoke. And smoke can be a lot of different things. Could be that the program runs or have stuck in a high CPU load. Could be that we're not getting any output at all. Could be that we have an assert that breaks, an in-code assert that breaks. Or it could be exceptions that are thrown, error messages, log messages, or output is like returning to -1 or something like that. So smoke testing is really good as a combination with these other types of testing. So let's imagine that you run a node server or something like that. Of course, you want to have a test case where you just start up the server and you do a couple of calls to the server, but you're not really interested in looking at the details of the returns. You just want to see if the server stays alive. So you're just looking for this big smoke things. You're not detailed in, I'm going to get this value back. You're more checking for this smoke stuff, what should not happen. So I did, for one of the games, a puzzle game, I did smoke testing. So I made a simple, I will not call it an AI, but an algorithm that played the game for me. And the algorithm could just play the game really, really fast. So I just made this self-playing AI play the game over and over again, just to see if it crashes. And on the screen, it just flickered super, super fast. And if the bug appeared, if I get a blue screen of death, then I know that this is problem. So that was one of the ways I tried to solve that problem of having all the frustration of running on and playing the game myself. So I write this autoplayer instead. So that was an example of all the smoke testing. So random testing is connected to this also. What if I put random input into the program? So let's say that for the add method, let's random A and random B. And then, we combine these two values and see what is the correct one. It's quite easy to do a plus addition also in the test. And then we just run this for a certain amount of time. In an hour, it can, run a couple of billion times or something like that, right? Or many billion times, I assume. But so random testing can be really good in some cases. And sometimes you can have intricate random input. So for instance, if you're creating a compiler and you want to see if the compiler is outputting the correct type of outputs, which would be a compiled version of your program, you can randomly generate real source code. You random, should it contain an if statement now? Should the if statement be comparing these two things? And you just have a set of a randomization to generate this input, and then perhaps it should not crash, or perhaps you calculate that all of these should compile or something like that. And it's also really easy to generate faulty input to faulty source code with errors that should produce an error. Like if I just randomize strings and send these as source code to the compiler, it should not compile those. It should find syntactical errors or compiler errors for those. Yes. So those were the different types of testing. A lot of different vocabularies today. Okay, so this is week 1. And next things, now we have had the course introduction and basics of testing. I want you to read the first 3 chapters of the book. The chapter 3 is more or less saying most of the things, the vocabulary that we've covered today. But I think these overlap my lecture in a good way. So you should, for the exam, both listen to the lecture and also read the book. There is a pre-recording on me programming in a TDD way. And this is a good way of learning about TDD on a really basic level for the ones that are not aiming for high grades. And this is also a good introduction for the ones who are aiming for the higher grades to start with Assignment 1, Part 2. There is a guest lecture with Max Beppe on their testing. He studied web programming in 2015 and has been working as a freelance developer. Hopefully, Max is also coming back to give a guest lecture this year or early next year or something like that about this freelance developer thing. There is this really, really old video on test-driven development on YouTube. I find I warn it a little bit. It's old. It's an hour long also. So, but get braced, eat some popcorn, and watch it still. And I will provide a link in your email so that you get access to CS quiz this week. Thank you for listening. Good work surviving.